Cool. So this is the way we talk about trees, right? And these are normal trees, meaning like they're not binary search trees, right? If it was binary search trees, like we would have to put the smaller, like the numbers that are smaller than this node to the left and the numbers that are larger to the right. But you can see both 9 and 20 are larger than 3, so it doesn't make sense. So we'll get to binary search trees later. But just note, like these are just what's called like binary trees, meaning that each node has at most 2 children. Okay? So these are just called binary trees. And you can see, right, our root node, our leaf nodes, right, direct descendants. Those are the main terms that we learned. And then that we can represent it, right, this is how we've represented our trees, is just what, this is the node, and then this is the direct children of that node, right, 9 and 20. And then 9 has a direct child of 15, and 20 has a direct child of 7. So then the next thing, right, is then how do we like move through this tree? How do we make sure we visit all of the nodes of a tree? And we have these 2 different mechanisms for doing so, right? Breadth first search and depth first search. Where with breadth first search, we move through in layers, right? And remember, kind of like one of the benefits of that is that if this hierarchy matters, like you care about the levels of the tree, like if they say represent distance essentially between like the root node and a leaf node, then that can make sense because it oftentimes also can represent like priority as to like how you want to visit them. Like we talked about LinkedIn connections or web pages, right? Like this being this being the Wikipedia article, this being a direct link, and then these being links to the respective pages, something like that, right? You might want to work from the root node out. Cool. Okay, so for breadth first search, if you think about it, like the main thing that I think of with breadth first search is we're moving through in layers, and then in terms of implementations, right, the data structure that we're just be thinking of like right away is a queue. All right, so meaning that the first element we visit is the first element, or the first element inserted into the queue is the first. We're processing it in order, right? First in, first out. So, okay, so then to go ahead with this, we'll just have our queue. And I'm also like, my brain is also telling me, okay, with a queue, I know I have to use this deck thing, and then I'm also going to have to do like the pop left, right? Remove from the front of it. So we'll do the queue, wrap it in this deck, right? The double-landed queue, have our root node, and then say basically while we have the queue, we want to get our node. So we want to pop it off the queue. And this is the part I always mess up. So just, hopefully I'm not going to do it now. But you have to remove it from the front of the queue, right? Because first in, first out. So, So queue dot pop left. And then we want to process. Then the next thing I think of is like process, right? Process the node. So what does that mean here? It's just like print the node and then add the children, right? So we want to do tree, so tree.get, right? So if I do 3, get these elements. So tree.get the node, and then we can say for child in this, and then we can kind of add the children to the queue. The one gotcha is like we want it to not throw an error if that element doesn't exist. So we should do .get node and then return an empty list in the case that this is null, right? And then we just add each of the children to the queue. So we'll do queue.append child. And I think that's it. So we're printing these out. Let's give it a shot. So let's think 3, 9, right? 9, 20, 15, 7. So that looks good. If you want to debug it a little bit more, you can do like print the queue as well, and then right, so you can kind of see just how this works. This is the first thing entered into the queue, add the children, 9 and 20, right? So process it, right? You can see we're popping from the left, and then 20, so 9 add its child, which is 15, and then process 20, and then process 15, right? And then finally 15's child is 7, and then process 7. So I just like double check it by like looking through it here. But the key things is like when you hear BFS, it's like layers and then implement with a Q, right? And then if there, to make sure there's no cycles, right, that if statement comes in basically like, should I, here's the node, but only process this node if node not in visited, right? And then you can, right, so you could also do this, just if you there's cycles. So if node not in visited, and then we'll declare visited to be a set, and then we'll say visited.add. It's not append, it's add with a set. Add the node to the list of visited. All right. And then just double check. That works. So this is fine. And then just quickly, DFS is really the same exact thing. What's the difference with DFS? DFS, the idea is kind of explore each path from root node to leaf node, right, fully before moving on to like another path. So, when I think of DFS, process individual paths from root to leaf nodes. And then the thing I always think is like keep digging. Like that's kind of the, right, you get to 9, keep digging down to 15, right? And what allows you to do that is implementing with a stack. So for the, let's just see like how quickly we can adapt this. This just this is really the main thing that changes, right? So we'll call this a stack. We can just have this be an empty list. We still have this visited, and then we say while there's a stack, we can print it. And then what's next? Instead of removing from the front, right, we remove from, right, we have this like, you have 3, let's say we have 3, and then we visit 9 and 20. 3, and then append in 3's children, so that'd be 9 and then 20. It will visit, you'll see it'll go down this branch first. So it will then process 20, right? And then 20 will add 7, right? So you're always going to be popping from the end and like pick up, 20 next and then 7, which doesn't have any children. So down here, we'll just do a pop. And we'll do, this is, did I call it? I just didn't call it DFS. DFS, it's a stack, and we'll just stack.pop. Right, so we'll pop from the front, pop from the back, and then if node not in visited, add the node, print the node for every child in tree.get the node, add it to the stack. And I think that's it. So the main changes I'm implementing is really the main one, like the only one that's really significant, is just stack.pop instead of stack.pop left. Right? And then we can print, and here we are printing the stack each time so we can see what's going on. Okay, so we start with 3, then we add the children, 9 and 20, and then this is the key thing, right? It then processes 20, right? So it's processing from the end next. So 20, then this adds 20's child to it, 7, and then it keeps going and processes 7 next, right? So 3 adds 9 and 20, then it processes 20, and then before it comes to 9, right, it processes 7. Any questions about those two algorithms? Feel free. All right, so definitely practice implementing this. We do have a lab on this, but I wanted to show you another way of describing a tree. So this is one way we did it, right, where we just use a dictionary. And then the other way, is like this. So you can just create, similar to a linked list, right? We had the value, and then we had the next node. But here for each node, we have left and right attributes. Okay? So you can see the way that I create this is I have my tree node 3, right? And then I have a tree set left equal to 9. I didn't have to do it this way. I could have, if we wanted to, we could do it like this. Tree node 9, right? Because it takes a, the value and then left. So I could do it like that. And then we do root dot right, right? So this root node, the right, maybe I'll copy this too. The right side should be 20, and then 20 has 15 and 7. So right, so this is to the left, 15, and this is 7 to the right of. Actually, this is a little different. It actually looks like this. So we could do it like either way is fine with me. Let's do this one. Sounds fun. Okay, so that's what this looks like, I believe, right? Because the root dot right has a tree node. Root dot right 20 is a tree node value of 20, and then 20 points to 15 and 7. Okay. And now if we want to, let's process it in layers again, I guess. So let's do breadth first search. So just note things are going to look basically the same, but just, we can't iterate through the children. Remember we did the child.get like node, and then we iterate through this list. We can't do that, right? Because this is actually, it looks like this, right? It has this object, and then it's like root dot right. This is one of the children, and root dot left is the other child. So how do we work through this? So it's not so bad. Basically, we still want a queue, right? And then we have the deck thing, because we're going to do our pop left. And then we're going to say, while we have a queue, while there's things in my queue, so let's put something in there. That'll be my root. While we have a queue, now instead of, we can process it, I guess. So we'll print the node, and then how do we get that node? We do queue.popLeft, right? So it's still removed from the front, and that will be my node. And then this is the step that we would be iterating, right? Previously it was something like for child in tree.get, node, but we can't really do that, right? We don't have a list, and we don't, instead we just have this root. So instead we'll do something like if root.left append, right? We'll do queue.append root.left. And then if root.right, or sorry, not root, if node.left, for this current node, if node.left, append the left child. If node.right, append the right child. Sorry, node.right. So this is just an alternate way. Like if you think about it, is this another way of capturing all the children of a given node, right? If there's a left one, the left child, add in the left child. If there's a right child, add in the right child. So append it. So let's just think about it. We have this root node that we start with. Okay. We add it to the queue. While we have elements in the queue, pick something off the queue, right, from the beginning, because it's breadth first search. If there's a left child, right, like 9, add it. Then add the right child. That would be 20. Okay? And then kind of you're done, right? And now we have a queue that looks like 9 and 20. Then we remove the first element, which I guess is 9. And then we process the 9, add 9's left and right children if it has any. I don't think it does. Then process the 20, add 20's left and right children. So that would be 15 and 7. Okay, so let's also print the queue. All right, so let's see if this works. Oh, and I should probably print, instead of printing the node, right, the node's going to look like this. Let's print the node.value. Oh, and yeah, it doesn't look super, but you can kind of see what's going on. I guess it's right? This is the node object. But first it's hitting 3. So first we're hitting 3. Then we're processing 9. So after we hit 3, you can see we're adding 2 elements, right? Those are the 2 children, 9 and 20. Then it must be 20 and 9. And then 9 and 20. Then 9 gets pulled from the left, right? So 9 comes next. Then the next guy from the left, right, is 20. So 20 gets pulled. And then 20 has 2 children of 15 and 7. So we have 15 and 7 that we add. Process 15, process 7. Okay? So it really is exactly the same algorithm. The only difference is that instead of doing that for child in tree.get node and iterating through it, q.append child, we're just kind of going through one by one. If there's a left node, append it. If there's a right node, append it. That's the only difference here. So the lab will, once you get to this trees depth walkthrough, that will walk you through kind of like how to do that, and then the lab kind of asks you to do it again. All right. Questions about this implementation or anything here? No? Okay. Let's do the next thing. Recursion. Sound fun? Okay, so what's recursion? Recursion is a function that calls itself. All right, so think about this function. We're going to have a function that like add up to 5. One way to implement this is, just have the numbers, right? 1, 2, 3, 4, 5. I know this feels like, why do we have to go through this? But just remember, like 1 plus 2 is obviously 3. Add the first 2 numbers, we get 3. Add this number, we get 6. Then tack on this number, we get 10. Then tack on this number, we get 5. Okay, so another way to implement this function is to, let's think if we wanted to like kind of make this generic. So have add up to n. All right? One way that we can write this, if you think about it, add up to n. So add up to, first we have this, 1, 2, 3, 4, 5. It is similar, right? If we can think of it almost like this. 1, 2, 3, 4 plus 5. And if we make this generic, right, if you put this in terms of n, this is really, one way to write this is really to say that this is add up to n minus 1 plus n. Okay? So this is the whole trick. So pay attention to this minute. All right. So one way to rewrite this, right? 1, 2, 3, 4 plus 5 is to say that, 1, 2, 3, 4, 5. Is to say that really we can rewrite this as add up to n minus 1, right? 1 through 4 plus n. All right? Now think about what's going to happen. If we implement this, this is going to be this is kind of going to be an endless loop, because then we're going to hit 0, and then it's going to go -1, add up to -2, -3, and keep going. So let me just show you. I'll kind of show you what we can do. I would just want to print out add up to n minus 1 plus n. And the way that we can implement this instead is we'll have a base case. So we'll say if n is greater than, I'll say 1, we'll return this. Otherwise, we'll return just 1. Okay, and we'll kind of see what goes on. All right, so now we'll do add up to n. N is not defined. N should be 5. All right, so you can see what's happening here, right? So basically, we get to add up to n minus 1, and that gives us 4. right? 4 plus 5. So this is really add up to 4 plus 5. Then this calls itself, right? So this is add up to 4. What does add up to 4 do? Like when I pass through add up to 4, that really subtracts 1. So then we get add up to 3, right? Plus the 4. And then we call the function again. That's again subtract 1. So we get add up to 2, right? Plus the 3. And then finally we call in add up to 2 minus 1 is add up to 1 plus 2. And then once we get to add up to 1, we get right here. N is no longer greater than 1, and we return 1. So really what happens when you do recursion is it's really 2 steps. I call it compilation, but I was Googling it. I think we should call this like building the stack. Is that you're always kind of like, you're doing this recursive call, right, where you build up a stack. So right, we have this add up to 4 plus 5, right, n minus 1 plus 5, which actually the same thing is, which compiles to add up to 3 plus 4, then add up to 2 plus 3, then add up to 1 plus 2. Once you get to this add up to 1, right, that's where we then finally can return something. This returns 1, right? Once I have this, then I know what does add up to 1 equal? It equals 1. So then what does add up to 2 equal? It equals 1 plus 2, which is 3. So I can say, I'll make this a little more clear. So that points to 1, right? This points to add up to 2 is really this value. So that is 3 plus 3, right? Add up to 3 is, I lost it. This was here. Add up to 2 is really 3 plus 3. Add up to 3 is really add up to 2 plus 3, right? So that's this value, 6, right, plus 4. And then add up to 4 is really this value right here, okay? So then we finally get 15. So what you want to kind of understand with recursion is it calls itself, right, what it's doing is kind of building this stack. It's compiling this procedure. And then finally it gets down to the base case. And then it can finally answer the questions. So the first step is, we call this add up to n. It's doing add up to n minus 1, which is add up to 4 plus 5. Then we get add up to 3 plus 4. Then we get add up to 2 plus 3. And finally we get add up to 1 plus 2. Right? It's just setting up the building blocks, right? The dominoes right now. It doesn't know what this is, doesn't know what this is, doesn't know what this is. Finally it gets here, add up to 1, and we call add up to 1, and it says, okay, you're passing through n. And we finally hit my base case. Once I have this answer down here, right, I can now answer what add up to 2 is, because it's 1 plus 2, right? So now I know add up to 2 translates into 3. Once I can answer what this is, that this is 3, I can answer what add up to 3 is, because it's 3 plus 3 is 6. Once I can translate what this is, that this is 6, I know what add up to 4 is, right? It's 6 plus 4. Once I can translate what add up to 4 is, I know what this guy is, right? It's 10 plus 5, and then we're done. So that's how recursion works, right? This is how the computer is doing it. The way I think of it, right, the way we think of what is the recursive solution is I like to think of like the definition, which is, you can kind of write it all out, right? It's 1 plus 2 plus 3 plus 4, right? Give yourself an example, which add up to 5. Add up to 5 is really add up to 4 plus that last number, okay? And so it's add up to n minus 1 plus this last thing. Let's do one more example. This will be reversing a string. So we can write reversing a string recursively. So how do we do this? Again, I'll give myself an example. So do hello. And then how would we, let's think about what this is. Reversing hello, right, that gives me O-O-L-L-E-H. So it's the same thing as, another way to work this is that it's O plus the reverse of E-L-L-O, right? The reverse of this string right here. Right? Because this thing right here is going to evaluate to O-O-L-L-E. All right? So it's the same kind of concept again. How do we define reverse? Reverse is the string, the last letter of the string, plus reverse of the subset, right? Reverse of string 2 through -1. Oh, sorry, -1. All but the last, right? All but the last, all but the reverse of the first. I think it might be all but the first one. Reverse of, yeah, it might be all but the first one. Yeah, let's do that. All right, I think that's right. So we move the last one to the front, and then we reverse the rest. And now, this again, right? We're going to kind of get this endless loop. So we need to set. We always need a base case, and here we can say if the string is greater than, and just notice again, we're passing through smaller and smaller subset each time. So if the string is greater, length of the string is greater than 1, we want to return this. Otherwise, like, what do you want to return? Well, think about it. If the string is just one letter, right, like the letter H or something, what's the reverse of H? It's just that string itself, just the letter H. Okay, let's see if this works. Oh, and I should return it, right? I didn't do it right, did I? I think is this for some reason. I think it's string to the -1. Miles, you got it?
It's you have it almost, but it's left plus everything except this. So it's 1 or 0 to -1.
It is to -1. That's to -1 right here.
Yeah.
So this is going to be reverse of, yeah, exactly, reverse of this, E-L-L-O. No?
Well, no, it should be H-E-L-O.
Oh, H-E-L-O, and then move the last letter to the front.
Yeah.
Okay, I get it. Right, because this will give me back L-L-E-H. Yeah, L-L-E-H will be the reverse, and then move this letter to the front. Cool. Okay. All right. Sorry about that. So again, you kind of, yeah, I like, again, like you see, I get confused by it. You have to kind of, if you give yourself the example, right, and then hopefully, think through it, then you can see we're just really coming up, like, what is the definition? Like, what is another way to reword, like, define string, or define reverse in terms of itself? Reversing a full string is reversing the subset and then moving one component to the front, right? The last letter to the front. Okay, reverse everything except for the last letter, and then move that last letter to the front. And it's again like one of these like countdowns, essentially, right? Countdown until the string gets smaller and smaller, and then finally it's just one single letter. Okay, because the reverse of this is now we're going to just take this component, right, and move this L to the front and reverse this. And then the reverse of this is, this, we're going to take this subset and move this L to the front. So you just keep doing that countdown. All right. So try to work through, I definitely read through the recursion lesson, see if it makes sense to you. Unfortunately, like when you get to binary search, the only way to really think about it is I think that's like the easiest way is through recursion. Like when you get to binary search trees. So just being able to read a recursive solution and see what's going on, right? It is important, right? So do try to spend some time with that. Let me see what we get. All right, so this is really what I wanted to go through was you can go through the tree's depth problem. And then this is kind of you implementing it. Then you can go through this recursion reading in the recursion lab. And then finally, binary search trees. And I'll deploy this reading. These are both essentially readings on it as well. So I'll deploy these. And then we can go through a lecture about this as well. All right, and then this is basically this is complete, essentially, in terms of the algorithm section. And we'll certainly go through more Python interview problems, but next we'll go back to SQL. I want to mix in, I do love this Roman numerals problem. This is Python, so we will mix that in eventually, but we'll start focusing more and more on SQL, okay, after today. All right, let me put you into breakout rooms. Please share your screens if you're, work together on this. Try to get the benefit of your pair.